So Gray, he's been doing his PhD in the mechanical engineering department with a focus on control systems, a little bit of control theory and experimentation as well. He came in 2013 from Olin College and HMC, which is an institute in Florida doing a lot of humanoids and all this crazy stuff that people do. And he was debating whether to come to Austin or not, and we brought him here. We're extremely lucky. He had worked before in an area called multi-contact, so we'll see that a little bit. It's more on the high-level planning of robotic systems for the DARPA Robotics Challenge. So he was a natural fit for the laboratory. And, but it was clear that humanoids are pretty, poorly performing. They're slow and they fall all the time. So he set himself into a quest of making humanoids and cirrus-elastic robots and exoskeletons to perform to their best. Because at the end of the day, they are flexible when you consider maximum performance. He won an SDRF, NASA SDRF in 2015. And since then, he has been funded by this wonderful fellowship. And then in the middle of his PhD, a new project came in. It was called Sagittarius. It's an Iron Man type of suit. And then he was determined to do impact there, which he will describe today. He has developed wonderful ideas. I don't want to spoil anything, but on simple, intuitive methods that accomplish the highest possible performance, whether it's maximum stiffness or maximum compliance into a variety of systems, subsystems, and whole systems, and so on and so forth. And I'm almost going to finish here because I know everybody's anxious about hearing him, but he has published in some of the hardest journals, Transaction Automatic Control, IJRR, IJHR, TMEG, and now he's set to publish something in IJRR as well as many conference papers. So without further ado, we're going to welcome here Gray. No applause yet, at the end maybe. So let's go for it.
Luis. So this is my dissertation on control strategies for series elastic multi-contact robots, and that is me in the Sagittarius exoskeleton. Fun fact, I can't actually bend my waist in that exoskeleton. So what is a series elastic robot? It's just any robot where in the transmission load path of the actuator, there is a series spring that allows you to sense forces, and it's got a bunch of other benefits. Safe human interactions often touted as a side effect of the force sensing. You can control the impedance. You can have the system comply to unknown terrain rather than being rigid when it touches down. There's some suspension-like effect. There's cheap force sensing. And then the Germans always highlight that it protects the motors when the robot falls over. It's impact loading reduction. So these robot controllers are typically arranged in a hierarchy, and each layer relies on assumptions about the layer below. And the big thing that got me interested in diving deep into the actuator control layer is that each of these assumptions is traditionally impossible. So the motion planning layer assumes that the robot is a rigid body system capable of applying instantaneously whatever torque you specify up to some limits. But the actuators have dynamics, so you can't actually do that. And the whole body control layer makes a very similar assumption about the force control performance at the level below it. I guess the motion planning also assumes that the whole body impedance control layer will make trajectories stable when they're not necessarily, that's not always part of what the whole body controller is doing. And then the series elastic actuator, the torque control, makes assumptions about the low-level model that aren't always satisfied. So the high-level model that we assume is pretty successful in simulations. So this is a clip from, or not a clip, but this is a picture from the DARPA Robotics Challenge. We were getting a virtual robot into this gator-like car. And the control problem here was all about maintaining the inequality constraints on those reaction forces that you're allowed to instantaneously control while moving your center of mass along your desired path. But those abstractions break down when we got onto physical robots here at UT. So this is the human robot, and what you're seeing here is the center of mass trajectory deviating wildly from the expected behavior. And this is a symptom of the high-level center of mass planner making assumption about the whole body control layer. The whole body control layer says it's going to keep the torso upright the whole time, and if it does that, it would produce inverted pendulum-like behavior. But in reality, the torso wobbles quite a bit because the best control we can get is really quite soft. And this really, it makes it a lot harder to control the behavior at the high level. And then at the next interface between the whole body control layer and the actuators, this is Valkyrie, the robot we work with at NASA JSC. And on Valkyrie, we want to have, you know, reliable walking behavior, which means having a good position control over the center of mass. And the stiffness you can do this with is limited by the responsiveness of the low-level torque control actuators. And so this, the model that we actually use to pick our stiffnesses doesn't have any knowledge of these uncertainties in the low level. I mean, it's like a model where theoretically you should be able to get as high a stiffness as you want in the center of mass. So that's another example of that breaking down. So the structure of this dissertation starts off at the planning layer, continuing on some work I did with the planning of human center of mass. And then it dives down into the actuator control layer, going really deep into robust control and the assumptions that need to be satisfied. And then at the very bottom, there was a little change of approach, and we took insights from learning about how SIAs actually work and brought those back up towards the robot control layer and exoskeletons. So this first chapter, about the center of mass planning. This is a robot I designed for a proposal with Luis. Never actually got built, but it looks pretty cool, right? This was a concept, and I guess I should skip to the video, but it's all about planning the center of mass trajectory, which is as extreme as possible. So to follow on to our work when there's a single point contact and there's only one thing the center of mass can do, and you can find the next time you need to switch feet by integrating forward and backwards in time to find an intersection. Here what we're doing is we're finding extreme trajectories when the multi-contact situation gives us authority to actually pick our acceleration a little bit. So we, instead of picking something in the middle, we pick an extreme and propagate that forward, and what we're finding is the maximum speed traversal of the path. One of the disadvantages of this strategy is that we relaxed the constraints on the foot switching. So at times, it does some unrealistic behavior of foot switching. Yeah. Oh yes, and this algorithm can tell you when it's impossible to cross a trajectory. If you have like a huge gap, you can't actually get across. It can tell you that. But ultimately, that foot, we stopped working on that when we realized that this strategy of taking extreme paths typically leads us up against the limitations of our model, which were the relaxed foot transitions. So this next chapter takes us more towards including series elastic actuator dynamics in the trajectory optimization. So the first one was kind of like a high-level center of mass path, and this one's more of a whole joint state trajectory from a start to an endpoint, or maybe a flexible endpoint. We optimized for velocity a lot at the final time. And what's cool about this is we were able to incorporate a linear model of the series elastic actuator behavior in a way that let us do iterative linear programming to solve this nonlinear optimization very efficiently. So it's not as bad as you would expect just based on the fact that it's a nonlinear optimization problem and you double the state size. The kind of behaviors this thing does, and I don't know if this is playing with sound. There we go, yeah. So it's very aggressive trajectories that wind up the actuator dynamics in anticipation of the final time where it's judged on how fast it's going. So this kind of anticipation of an event with the actuators storing energy is what this is a good strategy for. We also applied this in simulation to robot jumping. Maybe I should skip ahead to get rid of that audio. So here's a picture of the robot, and I think this is the part I'm going to see. Is that going? How's that going? You saw it moves, right? There we go. So we've got those actuator internal states visualized with these magenta circles, and you see it's bouncing back and forth to get it off the ground with as much energy as possible. Super slow-mo, I guess. And it goes slightly higher than the best outcome we can do for the rigid robot. So this model had had input and state constraints guaranteed satisfied by these trajectories, which isn't typically something that trajectory optimizers provide for series elastic robots. Typically, they just use the rigid model, and then it doesn't satisfy any input current constraints for the motor. Working with Binghan here, we also consider the problem of dealing with trajectories that don't satisfy those input and state constraints, but forcing the behavior of the system to always be safe by having the safety backup controller that kind of watches the distance to the boundary and takes over if you're going to drive it into the wall. So we think about the phase space region of which points can be safely recovered from. We approximate it with a bunch of Lyapunov functions. And for each of those Lyapunov functions, we solve this equation. The idea of a barrier pair is the combination of this B scalar, which is almost a Lyapunov function, but we subtracted one for minor mathematical details, and a controller. And this is a somewhat standard optimization approach where we parameterize the full state feedback vector and the inverse of the Lyapunov matrix as a new variable y, and then we solve for y, and it's linear in y. And this gives us our initial barrier pairs, and then we have a theorem where we can combine barrier pairs to make this bigger approximation of the safe region. And we implement the hybrid controller that pushes it back into the safe region when it gets close to the edge, as measured by that B function. So here we have an example with an inverted pendulum, and inverted pendulums have a point of no return where the gravitational torque is equal to the torque that the robot's allowed to apply. And these barrier pairs keep three different types of trajectories from violating the safety limits. All right. But this robust control stuff, this is based off of a guarantee from the model. So to get these guarantees, we need system identification to provide the guarantees. And typically, it's really more of a verification process afterwards where you kind of guess the model and scale it until the uncertainty is correct. So we had this hypothesis that the uncertainty information about the shape of the uncertainty could be learned from a type of frequency domain experiments where you have independent input signals for all of the inputs to this. So this antagonistic setup from Nick Payne allows us to provide independent external force signal and input current signal that have different phase and different relative magnitudes. And we think about the uncertain model in the three-dimensional log Nyquist plot, which is something that I came up with to kind of combine Bode plots and Nyquist plots. Here we think about a Nyquist plot where the magnitude axis is scaled to be a logarithmic scale. And what's cool about this plot is now you can imagine data points in three-dimensional space, and an uncertain model is just a geometric shape that includes all the data points. So this is like a very narrow tube up here and then widens out there. And so you can imagine that if we did the right test, we get a bunch of data points and then try to geometrically shape the best, tightest model to fit all those data points. So we took all this data, and because it's actually it's a 2x2 system, we can't actually plot the data points in this plot. But we have a linear model of what each of those things are, and we compare the predictions of the linear model to what the data actually was, and statistically show that the linear model's incapable of really expressing what we're measuring. So the simple explanation is that the clusters are very tight and they're far away when we use the best possible linear model to predict the outputs. So this kind of validates the hypothesis that there's information in this data set we collected that explains something about uncertainty, right? So it contradicts the hypothesis that no, the model was linear the whole time and there was no uncertainty to measure. So if we have uncertainty, we get this new interesting controls problem to fit, an optimization problem to fit the tightest possible model around all those data points. And we think about the models as, in general, these inclusions. So Y is an element of the set, A plus B delta C, where it's for any delta satisfying the standard norm limit on the uncertainty object from robust control theory. So it's induced 2 norm has to be less than or equal to 1. And we have this lemma that lets us re-express this as a quadratic form inequality. And this makes an optimization problem convex if we introduce some new variables that under a certain condition are related to the original variables of the inclusion. And this is our optimization problem, which maybe I should come back to that afterwards if you've got questions. It's really cool though. Essentially what this does is it fits a cone to all the points, but it's relaxed, just slightly relaxed around the origin to account for the fact that you've got noisy data. So if we actually did a really strict cone fit, these any data points that were actually near the origin would force the cone to be super wide, right? So we need to be able to ignore points that are near the origin, and this figure with Anstrom's quartet compares the ordinary least squares fit to the QIP fit for a couple of standard data sets. And using orthonormal basis functions, we can identify robust models for transfer functions. So I think the colors are a little bit warped here, but you can see that there's this kind of reddish model that's tight and this kind of bluish model that's not so tight, right? So this is, the reddish model is the QIP fit, and the bluish model is the least squares fit, and the uncertainty shape is based off of the parameter covariance estimate from least squares, for the least squares one, which is, it's a strategy people use actually. And both of them are scaled, the uncertainty is scaled, until they satisfy exactly the same constraints for each set of data points. So it's a fair comparison, right? So you can see that the least squares is definitely underperforming the robust fit here. And the uncertainty essentially comes from multiple models generating the data, and the models have different damping on these 2 points. And this is similar to a series elastic actuator, what we're simulating. All right, so we went down to that low level, and we got this technique for identifying robust models that capture the uncertainty in the system. But we discovered at the same time that this is the structure of the models we were using with that one delta object. It was not a good match for series elastic actuators. Because series elastic actuators, they really do have a pretty, at least on NASA's actuators, the spring does not really couple uncertain behavior from one side to the other side. It's really, the spring divides 2 systems in the series elastic actuator, and both of those could be done independently. And it's the motor side that really has more uncertainty because that's where the transmission is. So with a better understanding of the practical aspects of series elastic actuators, we can do a much faster, better job of getting a good series elastic actuator model with a couple of precision tests. A test for the inertia of the motor, a test for the damping of the motor, the spring constant, and the output inertia. And that allows us to address this challenge NASA has where it uses compliant actuation, but it needs a simple method to get higher stiffness for certain position control tasks. So here's our simple model in a couple, this is the Rosetta Stone figure. We are trying to get high stiffness position control in this actuator, and that corresponds to low compliance. We need to be stable in the presence of unknown environments. Our stability metric is going to be an extended concept of a phase margin. And the way we're going to do this is find and plot the CM model using these precision experiments, and also plot the joint inertia. We're going to relate the poles and zeros of the nominal CM model without time delay to the feedback control gains, which is going to be a 4-dimensional vector over the the motor position, motor velocity, spring deflection rate. That allows us to control the compliance of the actuator, the shape of the compliance of the actuator. Body plot. We're going to define the crossover point, that's the intersection between the closed loop actuator compliance and the open loop joint inertia. And then we're going to tune those poles and zeros to increase the stiffness without violating a phase margin at that crossover point. And then we're going to verify that the closed loop joint compliance is almost passive by looking at the phase. So here it is. This red line on the top represents the compliance of the series spring. And we've got a lower compliance with blue, the final closed loop joint compliance. And this means we're 2.4 times stiffer, right? What we've tuned is actually this Bode plot approximation without time delays for the actuator compliance. So we put this pole to zeros pole, and we got a shape that increased the stiffness at low frequencies. We designed this shape aware of the intersection, the crossover frequency, with the inertia of the joint. And we designed it to have a phase, and the relationship between, it's similar to the normal concept of a phase margin, but it's shifted a little bit in where the comparison should be. So it's actually comparing this phase here to 0. And that's similar to the phase margin. As this approaches 0, this pole becomes more and more oscillatory, right? So we've tuned that. And then ultimately the joint has all the non-passive behavior of the actuator compliance hidden by this intersection with the joint compliance. And the passivity is only 6 degrees, it's only 6 degrees away from being passive. So we know that it can be destabilized by springs. And those springs have to have stiffness within this range. And the springs have to be so perfect, they have to have such little internal structural damping that they are within 6 degrees of 0 degrees phase in their compliance in order to actually destabilize this thing. And in the data, we see that we are successfully getting this higher stiffness. And we also see that if we correct for the transmission friction effects, the data agrees with our predictions far better. So in both of these plots, we're looking at measurements and predictions. So the predictions are the dotted lines with the little white thing, right? So those are what we expect to have happen. And then we correct, it's much closer to our expectations. And so much closer that I think the transmission friction is really the biggest source of uncertainty in the whole system. All right. And also in the time domain, here we have the behavior we would expect if we were perfectly simulating a spring that is 2.4 times stiffer than the series spring. And here's the load torque we actually measure. And clearly at low frequencies and even at pretty medium frequencies, they are close together. So with that technique for shaping the compliance and that understanding of relaxed passivity in the Bode plot, I realized that I could also apply this to the strength amplification problem in exoskeletons, which is related to that Sagitt project that we talked about. So here we have a system that is actually kind of twice a series elastic actuator. We have a series elastic actuator driving the system, and then we also have this double plate flexure that acts as a series elastic cuff, and then the human connects here. So motor, bar, here we add some inertia, here's the spring, here's the cuff, and then in between the cuff and the spring there's a 6-axis force sensor which allows us to measure the torques on the cuff. So our model for this system, using that notation from earlier, is that it's got a series elastic actuator, and that series elastic actuator is combined with a joint inertia, so it's a repeat of the situation in the previous problem. But then we treat the closed loop compliance of that system like it's a closed loop motor system for a second bigger SEA that has the cuff spring. So we tune the behavior we want to see for the compliance that the human feels, the relationship between the cuff torque here and the position of the cuff. And that gives us our desired gains for the series elastic, that's the outer series elastic, the second meta-SIA. And then to implement that, we have this motor aspect of the second meta-SIA, and that's our closed loop objective for designing the first SIA's behavior. And I'll skip through this. We've got a kind of nifty way of setting up all of the systems using a procedural method. So our controller structure here, B, this is the full state feedback implementation for the inner SEA, so that's like before. And then we have the spring and spring velocity feedbacks for the cuff sensor, and a little bit of a compensator here to correct for the imperfection of the inner SIA matching the desired motor behavior we wanted. And then in the C block, this is a transmission friction disturbance observer. So previously I mentioned that transmission friction was the biggest uncertainty in the system. Well, we can actually measure all the inputs and outputs of the motor subsystem, right? We know the input current and we know the input force from the spring. So modeling that system as having a disturbance, we can create this simple observer to measure that disturbance and then compensate for it, which is a strategy that other people have applied to series elastic actuators, but not with the same model. So Nick Payne, you may remember, has a disturbance observer on his force controller, but his disturbance observer, the stability depends on the inertia that's attached to the SEA, so there's a minimum inertia. But here, because this is a totally autonomous system we're collecting a disturbance for, it doesn't actually depend on the motor or the output inertia if this is stable or not, which is pretty cool. All right, so preface to another Bodhi plot. We're trying to achieve a desired amplification ratio between the human and the environment side compliance the exoskeleton has. And we are worried about stability in the presence of the human and passivity on the environmental side. And we're going to use that relaxed passivity criteria again, where it's relaxed by phase. And our approach is to first design the human side compliance poles and zeros. And that's going to be limited by time delay in a pretty significant way. Then we will find the environmental side compliance. So that's actually what the joint compliance looks like with just the inner, the virtual motor system. That's what we're talking about. And then we will achieve that compliance by designing a SIA controller using compliance shaping again. Then we'll add in those nonlinearities, the delays in the digital filtering, and then we'll check for passivity and potentially iterate if we don't get the passivity we wanted on the first try. So there's really this adding nonlinearities portion is like it's not part of the nominal model, but it's really the key limiting factor on our performance. So here is our compliance ratios. In orange, this is what the human feels. And in blue, this is what anything touching the exoskeleton except on the force sensor feels. And what we've actually done here is we've taken the natural inertia for the exoskeleton and we've made it feel less compliant, but only slightly less compliant, or sorry, we've made it feel more compliant, but only slightly so for the human. And we're limited very significantly by the time delays. But then we've made it feel less compliant for the environment, which is easier to do. We've amplified the motor inertia to make it feel harder for the environment to move it. And this still increases our amplification ratio. But it's, I mean, we could plausibly keep reducing this and increase the amplification further. So here we demonstrated 8 times amplification, so if you compare 7 times the cuff torque with the motor torque, you see they're basically the same in the time domain. There is some oscillation. Here is my NASA advisor showing off the demo. So this is a pretty delicate plate flexure, and he's lifting up this 10-pound weight with it because the system's on. And then Thomas here, also from NASA, is showing off the second part of the demo, where you feel the increased inertia of the environment side, and then you look at that steady state relationship between your force and the environment force, and you feel that on this side it's 8 times stronger. All right, so moving up from those low-level successes towards the high level, this is a paper I worked on with Prashant, some of you may know. And this is basically looking at series elastic robots from the perspective of series elastic tendon-driven hands, which I claim they're just series elastic robots with more complicated transmissions. This work delved into a purely passivity-based criterion on whether the system is going to be stable. And the controller for this was defined ahead of time, so it was just an analysis problem on how big you could set the desired stiffness. But this is closely related to what I wanted to do on the Valkyrie robot, right? I wanted to be able to say, if you were setting the desired Cartesian stiffness for the whole body controller, the controller should be able to tell you whether that stiffness is viable or not based on its model of what the low-level system can deliver. So here we've got a linear matrix inequality condition on Ks, that's the series stiffness. Kp is a parallel stiffness, which Prashant was interested in adding parallel stiffness to the fingers. And Kd is your desired stiffness. I've also thought about how we might extend compliance shaping to go beyond, slightly beyond this passivity limit. And I don't think we have time to delve all the way into this math, but there is this quantity here which I call the dimensionless compliance, and it closely mirrors the shape of the poles and zeros you would set in compliance shaping, except now it's not quite as simple because the coefficients of the polynomial fraction are now matrices. But you could design these matrices to be symmetric, positive, definite matrices. So some things can carry over, and you have full controllability over what these matrices are. So you could potentially make them just diagonal matrices and shape everything to be just like scaled identity. Have all of like every singular value of this matrix doing the same little dance in the Bode plot to increase the stiffness. All right. So we also wanted to look at human augmentation exoskeleton control. And this brings us back to some of the ideas we talked about in the very beginning with the humanoids. And we are trying to combine the behavior of those humanoid controllers with compliance shaping for human strength amplification, because this system has to deal with friction cone inequality constraints. And it also has force sensors between the human and the exoskeleton that can allow it to do that same strength amplifying behavior. So our approach to this problem is based on another linear programming problem. This is actually the 6th version of the linear programming problem. So there was a lot of iteration here that's quite hidden now. But the take-home message is that we've put everything in terms of the torque vector to minimize the amount of variables the optimization has itself. And we've defined this virtual foot force. So the minimization is over the force on the hip sensor and the force that is other than the virtual foot. And basically what it's thinking about is a static optimization problem where the robot is held up by the 3 force sensors, and it's basically picking one of those sensors to give up on, and that sensor is going to take the load of gravity, and the torques are going to route the load of gravity into that sensor. So defining this virtual foot allows us to do human-led transitions where it shifts the weight based on what we think the human's weight distribution is, so that it can lift up its foot more easily. If you don't do this, then the human kind of has to pick up half of the weight of the exoskeleton every time they lift their foot. And to get this virtual foot, we solve another minimization problem, but this one has a simple solution. This is just a bunch of linear algebra to figure out the solution to this constrained quadratic. Another thing we're doing is we are designing our optimization cost based on a mental image of the strict priorities we want it to have. So because it has those cone constraints, sometimes the exoskeleton can't achieve all of its desired behaviors at the same time. It can't achieve simultaneously the correct force distribution on the feet and keep the torso forces 0, right? So when that happens, we want to be able to predict what's going to fail. And we do this by specifying a hierarchy of those objectives by splitting up each of the 6-dimensional wrench constraints into Cartesian subtasks, and then we prioritize those. But to keep the speed of the algorithm up, we don't want to implement a full lexicographic optimization because that would iteratively solve the problem once for each part of the cost vector. So what we do instead is we create these weighted one-norm costs that approximate lexicographic optimization. And what we're showing here is two different one-norm costs and one set of constraints. And we're showing off the fact that one-norm costs typically are sparse solutions. So here, the x-axis task is completely met. It's 0, right? And for the other cost, which prioritizes the y-axis, the higher cost for y-axis, the y-axis cost has been made 0. So by setting these one-norm weightings, often with like a factor of 100 difference between sequential costs, we've approximated priorities while keeping it very fast. And the way we included the compliance shaping here, we did not do the thing where we lowered the compliance of the exoskeleton side. We just increased the compliance of the human side. And we used a filter that looks a lot like a closed loop series elastic actuator to do that. It's got 2 poles and 2 zeros, which you can choose. And we use these filters on a transformed version of the cuff force we measure. So we correct for the frame transform. And then we apply the filter. And this is added in or subtracted from the torque we expect to have based, or the projected, the hip sensor force we expect to have based on our torque. So this is actually the objective function from that previous optimization problem. We adjust it to include this bias. And then the bias is itself set to avoid having a crossover with the minimum human, or the maximum human compliance in order to keep the system stable. Now, we could do this by measuring the minimum human stiffness, but we could also do it by just, as one function, taking this system and scaling it upwards in frequency until it shows vibration. And that's much simpler to implement on the actual operator. All right. So here is our video showing this. Here's that frame of expression here. That's where everything's projected to, even though the sensor's up here. All right. So we do an experiment here with 4 different tests. First, we put it in 0 torque mode and have the operator move around. The exoskeleton here measures the full weight of gravity. Then we turn on our torque compensator, which corrects for a lot of that. We add 25-pound weight and see the force goes up. And then we turn on our amplification and the force goes back down. And here I think he's doing squats at various angles and holding position. Later on in the video, it does fun stuff, but as Dragan pointed out, fun stuff which is not necessarily a test of the amplification behavior. Yeah, so this is a slide I'll show you next. Here is the behavior of those human-led transitions. So we can stand on one foot, the reaction force is all on the stance foot, and then when he puts his foot down, eventually, you'll see it zips over. Right? So the human-led transitions are actually pretty fast. And here the red image, that's where the exoskeleton thinks it's putting the virtual foot point. All right, and with a little bit of amplification. Even without the weight, the amplification helped him walk around. He can walk upstairs. This is the part Dragon said, well, what is this testing? But it's cool, right? Yeah. All right, so the result of the actual experiment here is that in zero torque, we have really high forces. Here's the forward force, the upward force, and the torque. And then when we apply gravity compensation, we really reduce the force, and the torque goes slightly, or the forward force goes slightly lower, and the torque goes way lower. When we add this weight, the torque goes back up, almost to where it was. Interestingly, the force is still very low. We think what's going on is that the legs falling straight down isn't entirely backdrivable by this weight. But when we apply the amplification, the forces go back down. So the amplification has worked. All right. On time. We added slides and I'm still like on time. So for SIAs, we've got some conclusions. When you add a spring to an actuator like this, one thing that you're doing is you're passivizing force control. So normally force control, because it increases the compliance of your motor, the compliance your output sees, it would normally be non-passive. But because you have the spring, you're actually making it passive again. The uncertain elements of the SIA are revealed to be mostly friction and time delay. The observers for the autonomous motor system are really powerful. And that, I think we should keep doing that. Although technically, we don't need the spring to measure and reject that transmission friction disturbance. All robots are series elastic and they're built to be super lightweight, so we expect this to continue to be relevant. Actually, just the other day I saw a video from Disney research where they were designing trajectories for super lightweight, flexible animatronic characters. I don't know if any of you read Google News or have seen this, but they were doing very similar things, correcting for the vibrations when they designed their animation trajectories for these physical robots. And series elastic identification, I think, is really best done with these precise tests where each test has its own feedback controller designed to amplify the part of the system you want to measure. On elastic-legged robots, series elastic-aware trajectories are not that hard. We should do them. With a good input trajectory, the whole body controller can actually focus on stabilizing the naturally unstable behaviors of standing on one foot or something. Passivity-based stiffness limits are essentially what you get, plus a little bit more if you're willing to really push it to the limits. I mean, all of these controllers where we got higher stiffness, they sounded aggressive, right? I mean, the non-passive behavior here, the actual, like, it's amplifying disturbances a lot more in order to get it just slightly stiffer. So I think from a practical point of view, if you're designing a new robot and you want it to accomplish a task, I'd make the spring stiffness naturally high enough to accomplish the task if possible. And the torque source model, again, revealed to be super unrealistic. If you are designing a series elastic actuator to be compliant, the best you're going to get is a reduced actuator inertia. And on exoskeletons, this is my latest favorite idea on exoskeleton design. I think we should move from the fully parallel mechanical structure that we saw on Sagitt to something much lighter with no springs, but still naturally there will be springs because the human isn't a rigid connection point. So I'm imagining these windshield wiper-like linkages to connect to the person and push on them while distributing the load so that you're kind of taking a bunch of small springs and compressing all of them equally. It actually increases your spring rate when you attach to the human to do this. And I'm imagining linkages that actuate purely torque on the human joints. And they don't have any parallel structure, no redundant structure. They fully rely on the human to have the joint. And I'm thinking this mostly because on that big Sagittarius exoskeleton, you could lift a 25-pound payload, but the exoskeleton itself is more like 100 pounds, it doesn't feel like it's worth it at the moment. So I think that the power to weight ratio for these exoskeletons is going to be really important for their practical application. All right. So here I've got a list of publications with, as Louis said, probably too many conference papers. And I'll open it up for questions.